In this video, we're going to take a look at some optimization problems. In an optimization problem, we're looking to find the largest or smallest value for a function or a criteria that we're looking at for a situation or a scenario based on some specified criteria called a constraint. So it's similar to what we did in finding the absolute extrema. We're doing applied max-min problems. So we're going to have to figure out what the function is that we're looking at. We have to take its derivative, set it equal to 0, and that will give us a max or a min. Find two numbers whose sum is 90 and whose product is as large as possible. So we want to maximize the product. Now we have to have a constraint. So the constraint in this problem says we're finding two numbers whose sum is 90. So I'm going to call x and y my numbers. So my constraint part of the problem, what limits what I can and can't do, is that x plus y equals 90. What I want to maximize is my product. So I know my product is equal to x times y. Now, just like we did with related rate problems, we don't like to have two variables when I'm going to be taking a derivative, because to maximize the product, I'm going to have to take that derivative. So I use my constraint to help me eliminate a variable. So I can rewrite my constraint as y equals 90 minus x. So now when I come down here for the product, my product is actually equal to x times 90 minus x. And then just cleaning that up a little bit so it's easier to take my derivative, I'm going to distribute. So I have 90x minus x squared. So now to maximize my product, I'm calling this p product. My p prime is the derivative. So that's going to be 90 minus 2x. I'm looking for when my derivative is 0 to get a max or a min. So 90 minus 2x. So I have 2x equals 90 and x equals 45. So once I know x, I have to get y. So I know y also equals 45. So the two numbers that add to 90 and have the maximum product is 45 and 45. Now I can check that and I can say, okay, 45 times 45, which is 2025. And if I check a couple other values, so let's say 40 plus 50 would equal 90, and 40 times 50, that would be only 2,000. So I can see that this did maximize my product. In this problem, it says we're going to use 20 feet of fencing to make a rectangular fence, and Chuck is using one side of his house as the fence, and he has a total of 20 feet. So if this is the house, and I build a fence off of it, it's rectangular, so I know opposite sides are exactly the same. And then I have a second side. And I know that my constraint here is the amount of fencing I have, right? I can't increase or decrease the amount of fencing. I have 20 feet of fencing, and that has to equal those three sides, 2x plus y. So I can write everything in terms of one variable. I'm going to rewrite this in terms of y, so y equals 20 minus 2x. Now I'm trying to maximize my area. So my area, in this case, my length times width is going to be x times y. I'm going to rewrite it in terms of just one variable, in terms of x, so I replace my y with what it's equivalent to, which is 2x. So my area equals 20x minus 2x squared. And then I want to take the derivative of my area, which is 20 minus 4x. Since I want to maximize this, I'm setting it equal to 0, so 20 minus 4x. And when I solve, I have 20 equals 4x, so x equals 5. And then plugging in to solve for y, 20 minus 2 times 5, y is going to give me 10. So again, I want to include my units. So this is going to be 5 feet by 10 feet. And this is going to maximize the area for that dog pen. In this example, we want to construct a box whose base length is 3 times the base width. Okay, so I'm constructing a box. I'm going to start by drawing my box. Okay, there's my rough sketch of my box. And it says the base length is 3 times the base width. So here's my base width. So its length is 3w. It told me that the cost to build the top and bottom of the box are $10 per square foot, and the material used to build the sides is $6 per square foot. If the box must have a volume of 50 feet cubed, determine the dimensions that will minimize the cost to build the box. So my constraint here is my volume equation. My volume is constraint. It's It's fixed at 50 cubic feet. And I know to get volume, it's length times width times height. So cleaning this up, I know 3W squared times H equals 50. Now to find my cost, we have to measure the area of our sides. So this back side here has an area of 3W times H. And I have 2 of those sides. So I'm going to multiply that one by 2. Then I have the other sides, which are here. And I have 2 of these sides. And those areas are W times H. So I have plus 2 W times H. Oops, sorry, that should be in green. And then we also have that bottom side, which is the top and the bottom here in this yellow. So I'm going to have 2 of those, which is 3W times W. So all of that together gives me my surface area. Okay, so the cost is based on my surface area. So now to get my cost, I know that the 2 sides are $6 each. So I have to do 6 times that whole amount, so I'm going to distribute here. So I have 6WH plus 2WH. And then the tops and bottoms are $10 each, so I have 10 times, and now I'm multiplying 6W squared. And that's going to equal my total cost. And this is what I want to minimize or maximize. Okay, so here again, I rewrote our cost formula, which is what we're trying to minimize. And I gave my constraint that the 50 equals 3W squared H. Now before I take my derivative of cost, what I'm going to clean it up to, I don't like having 2 variables. So I'm going to solve my constraint in terms of H. So I'm going to figure out what H is. So H is 50 divided by 3W squared. So now when I plug that in and clean up my cost, it'll make things a little bit easier. So I'm going to use C for cost. 6WH plus 2WH is going to be 8. 8 times 6, so I have 48 WH plus 60W squared. And then I'm just simplifying. I'm plugging in my H value, which is 50 over 3W squared. Cleaning this up just a little bit. 3 goes into 48 16 times. 16 times 50 is 800, so I have 800 over W, because W divided by W squared, plus 60W squared. And now I'm ready to take my derivative. Okay, so now taking my derivative, C prime is going to be negative 800 over W squared plus 120W. I want to know when that cost is equal to 0. So setting equal to 0, I have 120W equals negative 800 over W squared. Excuse me, positive 800. I added my 800 to both sides. So I have 120W cubed equals 800 when I multiplied both sides by W squared. So W cubed equals 800 over 120. So W equals the cubed root of 800 over 120. And simplifying, I have W equals the cubed root of 20 over 3. And that is in feet. Now we want to know what are those dimensions, so I also need to know my length, which is going to be 3 times that, and I need to find my height. Okay, so we know our width. So the length, we said it was 3W. So this is 3 times the cubed root of 20 over 3 feet. But we also need our height. And we said our height was equal to 50 divided by 3W squared. So this one takes a little bit of algebra to clean up. So my height is 50 divided by 3 times 20 over 3 to the 2/3. Remember, 2 is the squared. The third denominator, 1/3, tells me it's a cubed root. But this is not okay. So I'm going to multiply by 20 over 3 to the 1/3 power and 20 over 3 to the 1/3 power. So this is equivalent to 1. But what it's doing is, one, it's getting that radical out of the denominator, so that then it's something I can work with a little bit better. So now I have 50 times the cubed root of 20 over 3, all over 3 times 20 over 3. So my 3's wipe out. So I'm left with 5/2 the cubed root of 20 over 3. And we don't want to forget our units, so that is in feet. So we have our height, we have our width, and we have our length.